Morning. Can you hear me, those who are in virtual? Okay, so good to go. Welcome back, okay? We are back, huh? So this is our, William, as I know that this is annual, sixth annual conference. So we have started actually this from the beginning of the 2011, we did some conferences actually. Then later we end up with the STEM Day. Okay, so Provost Dr. Luis, I can see you. Nice to see you. Good morning. And Vice President of Academic Affairs also, Dr. Luis. Dean, Dr. Waynes. I can see Dr. Chair, Dr. Jiru, our department. I can see our IT Vice President, Dr. L, is here, and my colleagues are here. And ladies and gentlemen, good morning again. Welcome to 2021 annual STEM Day event. It's annual, as I told you. The Center for Nanotechnology at Coffin State University has been at the forefront in preparing students for the workforce in the areas of engineering, mathematics, science, and technology. The Center for Nanotechnology was founded in 2007. Although officially recognized as research center by the USM in 2020, we are located on the third floor of the Science and Technology building. We have trained hundreds of students who have gone ahead to successfully continue their studies in graduate schools or who have taken up jobs in industries. STEM Day at Coffin State University is an outreach program organized by the Center for Nanotechnology and sponsored by Constellation Energy, an excellent company. The program provides the opportunity for high school students and undergrads to explore the exciting fields of science, technology, engineering, and mathematics through research work during the summer break, a science fair competition which we will be witnessing today. So due to COVID-19 restrictions, the program was held virtually last year. This year's program is a hybrid one, with students presenting in person as well as virtually. We also have so many of our audience joining virtually. We hope that the presentation will provide a framework for the broadening of interest and training in STEM-related fields. The Center for Nanotechnology extends its sincerest appreciation and gratitude to Constellation Energy for ongoing support to the Center for Nanotechnology. For 11 years in a row, 2011 to 2021, the Center for Nanotechnology has been awarded the Constellation's E2 Energy to Educate grant. We hope to win the grant in the coming years as well. We are truly honored to have the Provost, Vice President, and Dean with us, and also Chair today. It is a true testament to their commitment to teaching and research in STEM. I would also like to acknowledge our IT department, headed by Dr. L. Hagan, for their support to the virtual portion of this program and all our online programs. Special thanks to Ms. Kelly Jackson and Ms. Melissa Rigby. To all the students, I wish you good luck in your presentation. We strongly believe that this will be an important step of your educational career ahead of you. May we have a fulfilling and successful event. Thank you. Now I'd like to give a welcome speech to our Provost and Academic Affairs Chief, Dr. Luis. Dr. Luis, floor is yours.
Thank you so much, Dr. Uden. Thank you. Good morning, everyone. It is a pleasure to be able to bring you greetings this morning, and I do wish that I could be there in person, but I'm actually expected to be on a call right now with the University System of Maryland, so I am late for that, but it is worth it. It is worth it for me to come to you and to congratulate those students who are participating in this event. It is worth it for me to recognize the impact of the Center of Nanotechnology at Coffin State University and our partner Constellation in your effort to bring forth the best in our students, to show our students that STEM is critical for the future. It is certainly worth it, because I would just have loved to be in that room to see all the students, the high school students, the college students who are taking their step into the field of STEM. You are greatly needed. Trust me, this is one of the fastest growing areas, and we need to make sure that we provide every avenue possible for students to maximize and to blaze a path into that arena. We do need to expand the number of minorities, the number of women who are pursuing field in STEM. And this STEM day that Dr. Uden and his team plans each year is a great pathway to help you to do just that. And so, wild horses couldn't keep me away from meeting with you this morning, and to say thank you. Thank you for your interest in STEM. Thank you for your research ventures looking at renewable energy, much needed. And Dr. Uden and your team, we greatly appreciate all that you do at Coppin State University. Greatly appreciate it. And I want to make sure that the students know you always have a place at Coppin. Always have a place at Coppin. As an HBCU and as a small comprehensive institution, our job is to make sure that we do everything to protect you, to make sure we guide you to your career path. We provide you with the resources to get there. In layman's terms, we got your back at Coppin. And so we encourage you to continue this pathway. Don't let this be a one and done pursuit of STEM. Let's keep this going. Thank you for making this an important day. Thank you for being on campus, and have a great presentation. It is possible I'll be able to log back on after my meeting ends later today. But thank you for having me. I wish you all a great day. Thank you.
Thank you so much, Dr. Lewis, for your valuable speech, and I really appreciate all of your support to our Center for Nanotechnology and Department of Natural Sciences. Okay, so I don't know, you can see that it's full of our students, staffs, and teachers also in this STC 120. So
I see that. Thank you.
Thank you so much. Next is our Dean, Dr. Wentz, please. You can talk anywhere, no problem. Yeah.
Good morning, everyone.
Good morning.
Welcome. For those of you that are new to Coffin, welcome to our beautiful campus. We are so pleased to have you. For those of you that have been here before and returning, welcome. I hope this proves to be a great day to you as well. And to the wonderful faculty, Dr. Uden, Dr. Jiru. I know his name very well. I call it almost every day. So I just want to welcome also our wonderful faculty and administrators here at Coffin State University. Dr. Uden has been a partner with the Constellation and Center for Nanotechnology, which he heads in this program now for 11 years. And I think he deserves a big round of applause for that. We thank the Constellation for their support of this program, as well as for the Center of Nanotechnology. The funding for this program has provided wonderful opportunities for students, not only here at Coffin, the undergraduate students, but also for postdocs, and very important for us are our high school students. Because we recognize the fact that anytime a student would give up their summer to participate in a research program, they are very serious and dedicated to the sciences. And so we welcome you with open arms. I hope that your summer experiences have been great, and today we are going to see the fruit of your labor. And so we're really excited about that. If we go back to the 11 years that we have now been partnering with Constellation, I think that it is just extraordinary that we have been able to hold that partnership, hold it in high esteem, as well as produce wonderful seeds. And I'm sorry, I see Dr. El Hagan there, and I need to recognize Dr. El Hagan because he's definitely he's an icon, actually, in technology for the state of Maryland and for higher education. So Dr. El Hagan, please.
Yes, sir.
We are looking forward to the reapplication, and we are confident that our successful partnership with Constellation will continue, as well as with the Center of Nanotechnology. We know that the Center of Nanotechnology continues to do wonderful things, to continue to raise the bar in scholarly endeavors, and especially in providing access and experiences for our students in research. And currently, I know that we have a number of students that participated this summer in that movement, as well as several students from a sister institution at Morgan State. But for our young people, for our budding scientists that are from high school, I want to talk a little bit, just take a minute or two and talk about the Department of Natural Sciences, where we have very strong programs in biology and chemistry that are second to none. Second to none. And what I will say to you is that a high percentage of our students are able to meet their academic goals, their career goals. They go on to complete and compete successfully in higher education, in medical school, veterinary sciences, PhDs, master's degrees. Anything that they want to do, they are prepared to do here. The other thing is that I am going to self-disclose and say that I am a product of Coffin State University. This is my home, Department of Natural Sciences. I was prepared here. I was able to compete at Rutgers State University of New Jersey in research. I studied at the Waxman Institute of Microbiology. I was able to compete successfully and earn my PhD there in microbiology with an emphasis in virology at a time when it was unheard of for women and minority students to do so. And I was prepared right here at Coffin State University. So over the years, and I'm not going to tell you how many years, but over the years, things have changed. For those of you that have not had the opportunity to go to this building, you are going to be astounded by the research efforts that are taking place here. The facilities for teaching science classes, the equipment. And when you talk to our professors and the staff members, the researchers, you're going to walk away in awe that all of that is happening right here in the corner of North Avenue. It is simply extraordinary. The other thing that you're going to learn as you walk through and check out some of our classes is that the faculty to student ratio, or it should be student to faculty ratio, is very low. So that means that you cannot escape someone not knowing your name, knowing what your goals are, and why you are here. And what you will find in that is that the faculty and staff here are totally devoted to making sure that you are successful. So for those of you that are now beginning to look at colleges and beginning to look at programs in the science, this is the place to be. I am a living testament to that. And I have full confidence that nothing has changed in the way of providing access to the sciences over the years. As a matter of fact, it has probably strengthened because of all of the tools that are at hand to stay engaged with our students. So please think about us. This is a wonderful campus. And I have probably gone over my time, but I just had to brag on Coffin State University, the natural sciences, our faculty and staff, and most of all on you, because you have made very important decisions to be part of the scientific world. And at a time when we need you, we need you, we need you, we need you. There are opportunities to be very successful, to make new things happen, to push the bar in sciences and technology. And this is the place to do it. Dr. Ubin, I wish you a really wonderful, successful day. Dr. Jiru, I thank you for all that you do to keep everyone and to make the programs grow. And to all of you, I wish you a very successful day. And I hope that come the fall of 2022, when I walk across campus, one of you are going to stop me and say, hey, I heard you speak at Science at STEM Day at 2021. I'm just so glad that you're here. Have a wonderful day.
Thank you. Thank you so much, Dr. Wentz, our dean. She's always our support in this department. Next is our VP IT Chief, Dr. L. Hagan, please. Floor is yours.
Good morning.
Good morning. Good morning.
Good morning, everyone. Good morning. Hope everyone is doing fine. It's a great day to be here. I'm Ahmed Hagan, the Vice President for Information Technology. I've been here at Coffin for 21 days. I cherish every day of those days because of you and the impact we see in you. When we meet you afterwards, you are successful in your careers. It makes us feel so good. Let me tell you this. I think I agree. You made the right choice of being here at Coffin State University. You made the right choice of choosing a STEM career. Those are two good choices that match each other. STEM, if you look into the world around us, most of the challenges we face today is going to be solved by you. Either it is climate change, right? We all hear about climate change, right? Either all this pandemic and the stuff we are suffering in the health area, either in cybersecurity and technology, the challenges we see. The world is built on technology these days. Thanks for the technology. That's what kept us humming over the last 2 years. So being STEM, and you like challenges, that's where you need to be. Being a Coffin is what's going to prepare you to face those challenges. You made two good choices so far. The third choice maybe would be of your own interest. A report just came out, an analysis of the Department of Education and the labor market states the following. The top earning jobs after graduation is in STEM. If you care about making money, which I think you should, right? That's what you need to do. STEM, 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 STEM. People who graduate from STEM have the highest earning jobs. Within 5 years, they pay all the debt if you have a debt. Compared to it, I'm not taking away from any other major. I'm an engineer, I'm a computer scientist, but I'm not taking that away from them. But that's the reality. The top paying earning jobs of analysis about 2.2 million jobs that graduated about 4 or 5 years ago so far are in STEM careers. So we made the right choice to save the world by being STEM. We made the right choice to be a Coffin because it's going to prepare you very well for those challenges. And you made the right choice for yourself and your families because it can make a lot of money. It's the best area to be at this time. Thank you for being at Coffin. Welcome to Coffin. Would like to see you during the day. Thank you, Dr. Jiru. I'm sorry, Dr. Odin, Dr. Jiru and the team. I see all the team here. Thank you all for having this day. Thank you, Dr. Owens. Thanks, Dr. Rose. It's a great time to be at Coffin. Make sure you wander around the building and see the facilities. You cannot find such facility anywhere else. In Maryland, I will challenge in many other big universities. Thank you for being here. Enjoy your day. Thanks a lot.
Thank you so much. Thank you so much, Dr. L. Okay, so next is our chair, Dr. Jiru. He's the chair for the Department of Natural Sciences, please.
Good morning, everyone.
Good morning.
So wonderful to see the future scientists in the room. And it's always a pleasure to also have him. And then also Dr. Al Hagan with us, because without their support, we couldn't have done what we do every day. Today is really a special day. What makes it special is, last year we were in the virtual world, and we did not get to see all of you, and many of you in person. But today really marks two important things. First one is really to kind of celebrate the work that our undergraduate students have been doing over years. Their undergraduate research, especially for some of them, are very difficult. We saw some of our students or graduates continuing directly to PhD programs without even getting into master's program. The credit goes to the undergraduate research they did. So I just want to really underscore the values, the time that you spent in the lab, that it would pay in time. It would pay in time. So keep what you are doing. I have seen in the labs, when I say in the labs, the Center for Nano is one of them, but we have also several labs and research centers where groundbreaking and innovative research is being done. And the one thing that I see in the students is the whole set. It's not only the skills that you learn, but it's also the competencies that actually you build while you are doing research. You know, public speaking, your interaction, your building network, not only within the department or across the university, but across, several institutions. And that is how, as an example, one of our graduates happened to receive a fully paid PhD program at the University of Minnesota, just because of that network. And then the other one, she just completed at the University of Florida, Charlene in chemistry. We celebrate them because they did all this through the network that we created over years. So that's why I say we celebrate for the work that you are doing, which definitely brings the evidence. For the future STEM scientists who will be joining us, I don't want to paraphrase what the dean and then also the vice president beautifully articulated, right? But I will add one thing. When we say STEM is the future, it indeed is. It indeed is. If you look at some of the reports nowadays, the inequality and the injustice in STEM is beyond what you can imagine in the United States. It is less than 10% of the African Americans and colored people in Germany who are in the STEM field. So you would ask, who is the 90%? Who is in the 90%? And how did we get here? How did we get here? We don't want to dig into history, but the reality is there are several reasons. So this is a time that we really need to change the color, the numbers. And I'm sure over the last 2 years, you have seen some of the initiatives through federal government and state governments, where now there is indeed a special place, especially for HBCUs in STEM. And as we speak, the National Science Foundation has rolled out over $35 million worth of projects just for HBCUs in STEM. Why am I saying this? Because first of all, we have to really accept the reality where there is indeed inequality and injustice. But unless we walk to the opportunities will not walk to us. So that is why all of us in this room, and then also in the virtual room, this is our moment. If we don't use it, we're going to lose it. So that is why, especially for our high school and the elementary school students, see the light at the end of the tunnel. It is brighter. It is brighter, but we have to work together. We really have to work together. And then that is what we're going to provide here at Coffin. We have the resources. We have a good heart. And more than anything, you have the most hardworking faculty. The most hardworking faculty in the department and then at the university. So you have our commitment. When you come to our rooms, when you come to our department, we do not ask you what you would like to major. What we ask you is, what would you like to become? So that we help you get there. We are more interested about your destination, not the bridge to the destination. The biology degree, the chemistry degree may give you something, a degree, but it doesn't take you to that destination. So we ask that question whenever you come to our if you want to be that engineer or that chemist, pharmacist, or physician, then we start from the end in mind, and then we work with you throughout. That's why we are there with you during your MCAT preparation, PCAT preparation, and other entrance exams. We also see if you satisfy all the requirements before you leave the door. We have a purpose. We have a purpose. So when we say Coffin is a nurturing environment, and the Dr. Owens really put it beautifully. You don't want to see outside. You have a living example in the room. Seeing is believing, as we always say, right? So this is the kind of environment that we require. And then this is what the center and then the other laboratories have been doing over the last years. So we'll continue with this journey. You have our promise, but we need your commitment. We thank you, Dr. Udin, for organizing this yearly. And then we also are really very much grateful for Constellation for giving us the funding support that we really need over the years. Thank you all. Have enjoyed the
Thank you, Dr. Jiru, Department Chair, for your valuable speech. Now our time. Okay, so this time, this is the first time our students, not only high school students, undergraduate students, and the graduate students. So graduate student means our sister institution, Morgan, a couple of students, they work in our center collaboratively, they are presenting. And undergrad, there are seven students, and also high school students work there. So they will present their own work. So now the time for presentation time. So undergrad, then high school, then graduate student will present. One by one, I'll call them and please come. First is Balvin Richard. Will talk. Please come in. Yes. So you have a 12 minutes, and 2 minutes is question and answer. So, Ms. Kelly, please. You can walk around here and talk. Okay.
Hello, good morning. Sorry. First, I would like to thank everybody for coming out. I know Coffin is like my second home because I'm an international student from Jamaica. So every one of the professors here has groomed me into the person that I am now. I could start from, if I continue calling names, I wouldn't even stop right now. So I wish I could inform you, entertain you, as much as I can do. So my objectives. So I'm doing fabrication of dye-synthesized solar cell using cryptophyllum canicum, which is also called star apple. So a lot of persons get this mixed up and think it's like gimbalin or star fruit, you know, the one that looks like a star. But this is actually that right there. This came directly out of a freezer because I had to travel it from Jamaica. So I had to freeze it so I could get it over here. So, okay. All right. Sorry about that. So these are like my objectives. So the first one is like everybody wondering what is dye-synthesized solar cell, right? But before I even go to like what is dye-synthesized solar cell, I'd like to really stick your mind with like what is a solar cell. So a solar cell is basically I would use it as a mechanism because I don't want to also use it because a plant could be a solar cell as well. even the grass outside, it is taking in sun energy, right? So it is anything that converts electromagnetic energy into a different form or source, like any different type of source of energy. Understand? All right. So let me.
Okay, I can help you. You can talk.
Okay. All right. So this is what I call a TCO sandwich. A TCO stands for transparent conductive oxide. This one is mostly made from fluoride, dope, tin oxide, the one that I use. Some are made from zinc, some are all different types. So at the top layer, you know both sides you're gonna have an anode and a cathode. So the anode is where we have the titanium dioxide and where we have the dye. So as you hear dye, so dye synthesized solar cell is using organic or inorganic dyes to generate electricity. Understand? Yeah. All right. So in the middle of it, you know when you make a sandwich, right? You know, some person put like lettuce, tomato, onions, anything in the middle, right? So for our sandwich, we'll have the two layers of TCO glass. One is an anode, one is a cathode, and in between it, we put electrolyte. The electrolyte is an iodide electrolyte, so we can transfer electrons from the anode to the cathode. Understand? All right. All right. So this is more like what is star apple, or what is chrysophyllum canito. So I couldn't really put a lot, but it's a tropical tree that grows to like 25 meters tall. So for me to get this fruit, somebody has to really climb the tree because this tree you can't pick it. The only time when it drop on the ground, or if you get it on the ground, is when it's spoiled. So when it's not good. So I had to make somebody really climb it. And this is not regarding some of these parts is not regarding dye synthesized solar cell. It's just that parts that you can use it for, because this also helps with the treatment of gunpowder at the bark. This also helps with, as you can see pneumonia, you can see hemorrhages. I'm not only just trying to talk about my research, but I want to show that you can also use this fruit to venture into something. I know a lot of seniors in there that need thesis, and you could even use one of these and just do anything that you feel like you could get success out of. All right, so this is just where I got it from. So I'm normally from Kingston. I'm from Kingston, and I had to travel to this farm village to try to get this fruit. So I had to travel on this road. They call it flat bridge. This is the most dangerous bridge I know, because the water sometimes rises, and if you try to cross it, it will push the people into the river. So that's one of the farms right there. It's like a wilderness, I would call it. It's just a lot of bushes, a lot of everything. So next. All right, so my extraction process. So I split my extraction process into 4 parts. So the 4 parts is that, remember I tell you that before I carry it over here, I have to freeze it. So I have to go basically do that by so I got to thaw it, I got to peel it to get the other layer. And then because this fruit you can't get juice from it as a pulp, I have to use a solvent to extract it. So, and then after is evaporation, which I do 2 different types of vaporization technique, which is boiling and one is evaporation. You understand? All right, so we go more into as you can see, this is frozen. You can still, if you can look at the top, you can see like a little bit of ice at the top. So this is frozen. So I make this thaw in like room temperature. And room temperature at sea is 22 degrees Celsius. So I let this thaw for 8 hours. That's like really long because But it's worth it. I got something that I could show you, so I had to peel it, get the edible part, take off the actual insides, and next slide will show you more. So this is how it looks. So this is when I peel it, you see how inside it looks nice and boiled, like color, purple like color. And then this is it with the solvent, and this is it after. So the pigment is extracted from it. Understand? Alright, next. Alright, so this right here is that I show you that I use two types of vaporization techniques. So the first type is boiling, and the next one is evaporation or passive evaporation. So the reason why I did this is that I was wondering, okay, if I boil it, I know I'm going to break some of the bonds. But, and you know, boiling starts from the bottom, evaporation starts from the surface. So I wanted to see which one would give me the best result. Alright, so let's show you how we prepare the slide. I wish I could bring like something to really show you exactly, but so this is the slide preparation process. So first, I have to make the titanium dioxide into a paste. So I'll mix that with acetic acid and soap water for smoothness. Then I put it on a spin coater. So the spin coater will then smooth it out. So I have a thin layer. And this right here is on the anode side. So then you have the drying. So I have to dry it. So to dry it, I have to put it on a hot plate so that I could get it to stay formed nice and flush. All right. Now, dye pigmentation. I have to take the dye that I have and put it on that anode layer so it can fuse, and that takes like a day to get it nice. Then for the cathode layer, I use graphite. So graphite, like a lot of females use nail polish, right? So I have to use it like a nail polish and basically polish the other TCO layer on it. So, and then I add, as I said before, the sandwich, I add the electrolyte in the middle. This is just saying what I did, but we can move from this one. All right, so right now it's like, I'm trying to test how much energy it gathers, right? So lamp tuning is the most important process. It is even more important than we getting the result. Because if I use like 50 watts, I'm not going to get a lot of light. So this is the most important part. Because I could have a good sample and I didn't tune the lamp good, and it's not going to record good data. So it's like, this is the most efficient part. And the second part is just adding the electrodes. So I need 4 electrodes, 2 on the cathode, 2 on the anode for testing. After that, this is my results. So as I said before, one was passively and one was by boiling. So the top one shows that when I boiled it, the efficiency was lower. So I get 0.16, 0.06, 0.02, 0.02. But after I just leave it, let it passively evaporate, I got a higher efficiency in average of 0.1, 0.3, 0.17, 0.05, 0.07. So this is the graph that's showing the top graph was mostly, if I pronounce it right because of my accent, it's mostly a measure of resistance, and square is like resistance of a surface. So we plot in the resistance of the TCO layer with the dye. Understand? And frequency. Okay. All right. So the last part is voltage over current, and we have degrees and frequency. Any questions?
Okay, so yes, you're on time, so I can take one or two questions. William, get for Chikarik's presenter. Any question? Go there. Yes, please.
Yes, sir. I like the presentation, great presentation, very good approach. Apply it to it, and it's very good. What is the second step on that?
The second step of this. So,
Like the identification too. More interested into like the actual group itself. Well, I'm very sure from what you said, there's a lot of potential in there. Yeah.
so the next step is, my next step is mostly to see what I can really get out of the group for every aspect. So I know that it regulates like diabetes. So I wanted to wonder what's the effect on the eye if you eat this fruit, because diabetes is prone to like vision loss. So I wonder if this person eat this fruit, will the vision get better or worse same way? So even as you say angina, it actually helps with treatment of gonorrhea. So it's like there's a lot of steps I wish I could test for it. As it's like it's more limitation to time, and so I wish I could reach a level that I could test all of these aspects.
But when we look forward to the things we learned, I think this is going back to the herbal medicine, which is pretty much used like in nature, like down like in Jamaica. So it's being known like for a while, right? But it's very I'm pretty sure this will like, flourish into a lot. It's a good job. It's a good job.
Go for.
Can we look at your graph?
Sure.
The efficiency.
Sure. Up one.
The efficiency.
The table for
Yeah, the table. Sorry.
Okay.
So I'm trying to make sense of the efficiency. How do you interpret this? How is 25% efficient? How is it? Is it out of one? Is it out of what?
It's the efficiency is measured out of 100%, but you have to put in like so as a natural silicate solar panel, the maximum efficiency you would get out of that is 22%. That's the newest one. So normally, if you go fully solar, you're only 10% efficient. If you really have the money, you're like 22.5% efficient. So this is on a small scale, and we have a lot of factors that affect this efficiency. So when I would look at this, it's just like more of an illustration to see how can I get this.
You can go.
Normally, a dye-synthesized solar cell, 0.6% is like, if you have a 0.6%, everybody will probably praise you for having like something like that because it's just natural.
Okay, thank you so much for the time being. You can take the questions. Thank you. Okay, our next speaker is Beatrice Ashanti Beatrice, please go there. Ashanti, yes, Ashanti Beatrice, please. You can take it like what you want.
Hi, working there.
Okay, loudly.
Can you hear me, guys?
Yes. Now it's fine.
Better.
Good morning, and thank you all for coming out. So I'm Beatrice, and I'm going to present on the dye as Delvin did, but mine is with an artificial dye called Berlin. Right?
Okay. Yeah. Next.
All right, so I'm going to talk about the solar cells first. All right. And Delvin, well done, good job. You did a good job. About solar cells, okay, so the dye-sensitized solar cell, as we all call it, DSSC, can produce electricity under low light conditions, right? It changes visible light into electricity, and this method was discovered in the 1960s. All right. So for this research, you can either use both natural dye or artificial dye. In Melvin's presentation, we use a natural dye, but in mine, I use an artificial dye called Golden 60. All right. So the process or the materials used in making the slide for the experiment is the titanium dioxide paste. All right, so the materials you need is the titanium dioxide powder, and then we have acetic acid, we have the soap water. So the measurements there depend on the number of slides you want to make or you have to make. Then that is a step. All right, so you mix those three materials together into a fine paste. Then you put it in the spin holder to spin. All right. All right. So this is the result. So after putting it in the spin, holder, this is what you get. This is how the slide looks. All right. And as Belvin said, this is when you put the graphite coat on it. All right. That's how it looks like. And this is me coating the slide, this part, with the dye. All right, this is me putting the dye on. But now you have to leave it for maybe 24 hours or something. But this is me just putting it on like a few minutes. All right, so this is what I'm going to talk about. That is the vitamin 6G, iso phenaldehyde. All right. Right, so what is rhodamine? All right, so it is a chemical compound and a dye. As I said, it's an artificial dye that is often used as a tracer dye that is found in water to determine the rate and direction of flow and flow. Right? So basically, this dye can be used for so many things. All right, though it's an artificial dye. Yes, it can be harmful at some point or at some quantity, but in research, it is very good, all right? So it is used or found in textiles, it is used when printing papers, it is found or used also in petroleum products dyeing, right? All right, so with the help of Tolu, who is doing her PhD at Morgan State, these are some, not all, but some of the rhodamines she is working on and I am helping with, right? So I couldn't make everything here a lot, so just some of the points I have to put there. And all right, so this is the molecular formula for it. As you all I know most of us are taking organic chemistry and Dr. Sylvie are here, so this is the what? Skeletal structure, correct? Right. And then we have the molecular weight that is soluble in water, all right? And then it is used in the synthesis of the dinuclear glutamate complex, right? So these are the results I found using after doing the experiment, all right? So please bear in mind, we had a lot of results, but because of time, I couldn't put everything on the slide. So these are some of the results. The results of the lifetime, right? And then that is over the intensity over time, all right? And also what we did notice was that with the vitamin 60 G, right? What we found was traces of what? Copper, all right? So what we did was, since it was able to detect copper, what we did was, when we were measuring, we had to measure it in two separate. So we had one without copper, obviously it has copper, and then one we added copper to see if it would make any difference. And as you can see, there's not really much difference because already there's copper in it, right? So even if you add copper, there's not much difference, right? And this is the intensity over time. Okay. All right, this is also the result for the IV measurement, and it's over current and voltage. All right, so this is the result with copper, and that is it with that copper. All right, so as you can see, there is not much difference. And also with this, it also shows traces of mercury, all right, but I didn't put it on because it would have brought a more, I had to also back it up with other side. So that made that slide a lot, but as you can see, it almost has the same results, all right, as the IV and at the lifetime, all right. So these are some of the images and the instruments we used in the experiment, all right. So this was what it was, all right. So what Julie does is the page she finds, the dye is how she labels it. So this was found on page 25. So that's why we have the name P25. All right, this is a titanium dioxide powder. That's how it looks like. And this is the spin coating. All right, so this is when you're about to put it in, right, to close the slide. This is how it looks like. And when you cover it and it keeps on spinning, this is how it is. All right. And this is the solar sensor. So this is how it is, as Kelvin was trying to explain. You have the ball coat, you have the nano, and then you have the cathode, right? So that is how it is. And then when you're ready, you take that out, slide, and then you measure, you get your results here, all right? So that is it. And I want to thank Dr. Emmanuel Gant, who was so helpful, Dr. Udin, and also Tolu, who also gave me the opportunity to work with her on it.
Thank you, Beatrice. Yes, Beatrice worked in the summer, and then yeah, he worked in the summer, and then here he is accumulating data. Also, she is working with Tolu, Morgan State grad student. So hopefully we'll have a paper with her one day. Okay. Thank you so much. Is there any question for one? Okay.
What is the objective to add copper?
What is what?
The objective to add copper.
To see if it will actually have any result, because if it already has copper, it shouldn't make any difference if we add copper.
Yeah, because I don't see any difference in between the two.
Right, we wanted to see, that is what that was our objective, right? To see if it will actually change or make a difference, right? We were right with it has copper and we add copper, it shouldn't make any difference. Okay. And we added copper to not just this, other dyes as well. So yeah.
Like where the copper came from? The main structure of the dye is the isophthalate, right? So it's basically like organic compound from phthalic acid. So where does the copper come from in the original dye?
Where is the copper coming from?
Yeah.
Oh, the copper is coming from the dye. Right. From the isophthalate, that's where it's coming from.
Yeah. You have something with the isophthalate?
No.
Because the isophthalate by itself doesn't have any copper.
And so it's like, yeah, I can.
Okay, no problem.
Tolu can answer. She will talk more.
Okay, so the compound using 60 is that we use, and we attach and how the height because the height of fashion is talking about. So what we did is after synthesizing this dye, we reacted with different cations, different metals to see which one would be selective. Yes. Right. So we decided to react them with different metals, and we tried various of metals, but this compound was selective for copper. So this compound is a non-fluorescent compound, yes, which is colorless. But when it comes in contact with copper, it changes to pink to show the yes, transition, and also become fluorescent when come in contact with copper. So copper binds with this compound. That's what she's trying to say. Yes. So after doing that, she now did some experiment on solar cell. That was why she added copper to
Thank you so much. Yeah, yes, it's a breathing complex proper. Thank you. Thank you. And I'm pretty sure she will do the some work here as well as Morgan with Toby. Okay, so Toby is coming to talk also here. So next speaker is Chika. Chika is my wonderful student, one of course, betrays everybody. So she's going to talk about the synthesis and application of silver nanoparticles. As you know that Chika was working another project also, isn't it? That is microplastic. Okay, let's go with the Chika. Okay, let's see what she talks about silver nanoparticles.
Good morning, everybody. Can everybody hear me?
Yes,
Okay.
loudly.
So,
Okay.
my name is Chika, and Dr. Dean has said I work with silver nanoparticles and also with microplastics. So I was conducting two research projects at the same time. But today I will talk about the synthesis and applications of silver nanoparticles. So I'll go over the background of them, the method that I use to synthesize them, the characteristics, the antibacterial mechanisms of silver nanoparticles, and then applications. So silver on its own has been used in history. It has been used to control infections, to treat ulcers, and in wound management. And silver nanoparticles are also used in various fields. They are used in food and management, in agriculture, in consumer products, and in various industrial purposes. And that's because of their biomedical properties. There are various methods that are used to synthesize silver nanoparticles. The method that I used was chemical reduction because this is the most common method and it's the easiest to do in a lab setting. And that involves using reducing agents. The one that I use is tannic acid and trisodium citrate. This is a technical process of what I did to synthesize them. So I used tannic acid and trisodium citrate, and I added them together. And with that mixture, I set it to boil, while also setting silver nitrate to boil as well. And after that, I combine them, and then I let them boil together. So at the end, you'll get a yellow color on a gradient, and the longer you keep it, the darker it gets. So the color that I was usually looking for was pale in color. And depending on the concentration of the reducing agents, trisodium citrate and tannic acid, you'll get a darker color, and the reaction will happen really quickly. So sometimes it will be a clear solution for like 20 minutes, and other times it will turn yellow in less than a minute. So after I synthesize them, I would characterize them. And I don't have a picture of the instruments that I use, but I use the UV photometer and the DLS. And with those things, I basically wanted to find the absorption and the size of the diameter of the nanoparticles that I'm using. So I did various trials. But I essentially did so many trials because with silver nanoparticles, they are more effective and toxic against viruses, the smaller that they are. So I wanted to get so basically I wanted to get an absorbance of less than 1 and a diameter size that was around 30. So the smaller that the particles are, the more toxic that they are. So in each shot I got around 20 nanometers in size, which is a good amount if you want the particles to be more toxic. Now I'm working with silver nanoparticles because of their antibacterial mechanisms. So silver ions are able to adhere to the cell walls of organisms, and that can cause the breakdown of the cell wall, which is why they are so toxic against viruses, fungi, and bacteria. So this is a diagram of how the silver nanoparticles can cause cell membrane breakage of the cell wall, and they can cause damage in the cell. And they have various applications. They, as I said before, they are used in the environment, in textiles, they use in cancer research, in needs like immunization, and agriculture and other various industries. The application that I am most interested in right now is in water treatment, because silver nanoparticles have antimicrobial properties. They can be used to treat water, especially wastewater and drinking water. And this is a diagram of a filter system. The silver nanoparticles can be attached to the blotting paper here. And so if the live bacteria go in, they are killed by the silver nanoparticles on the paper, and that dead bacteria come out. And this has been proved to kill various bacteria such as E. coli and other things.
Good.
And they can also be used in household water systems like Brita filters and things like that that you connect to your sinks. They can be used in a way like this where they are attached in the filter and can be used in a similar way where they filter out the bacteria that are contained in tap water. So I still have a lot to research. I didn't start the process of applying the synthesis that I've done to the water treatment, so that is still something that I'm working on. And I would just like to thank Dr. McKee and Dr. Nog for helping me conduct this research. Now as a freshman here, I didn't have any idea of what I would do, but Rudy pulled me aside and said I should work with him. And so now I have additional work with microplastics. And so I am quite busy.
Okay, good. Thank you. Thank you. Any question? Any question? Yes.
Well, I haven't started that research specifically, but it would probably tell the amount that are still there. Because they're supposed to be caught by the filter paper, so it's never left over. You see how many that is still in
Okay, any question? Okay, thank you so much. Okay, Chika. Good job. Our next speaker is Ruth. She'll talk about the nanotechnology and gold nanoparticles. So, Ruth, go ahead. You can talk over there. You're okay? Oh, you want somebody? Oh, you're not coming up. Okay, so next speaker next. Who is talking about next? Mia, you can come. Okay, we have some difficulties with her to present. It's the wrong presentation, so we'll go. Okay, so next. Okay, we'll go next presenter, Nia. What Nia will talk, and be ready by next. Okay. Can you go ahead? So she'll talk about the identification of microplastics. So we have a actually ongoing research going on with our department. So we are trying to apply NSF grant for CREST grant. So some of the data, prelim data, actually, she will present. Let's see that what she will present. Okay, Nia, go ahead.
Good morning. My name is Naya. I'm currently a junior and I'm a chemistry major here. So I'll be talking about microplastics. Microplastics are small pieces of plastic, and to be considered a microplastic, it has to be smaller than 5 millimeters, and typically you can find them in a lot of places. Some common items that you may recognize where you can find microplastics: skincare, glitter, the filter and cigarette butts also are microplastics. Tennis balls, the coating on the outside of them. When it sheds, considered a microplastic. Synthetic clothing, and your plastic water bottles. Once your bottles get broken down, they do eventually turn into microplastics and they end up in the Why are microplastics a problem? They do affect the food chain and fish and animals specifically. They block their digestive tracts, they diminish the urge to eat, and if the animals aren't eating, they die. It affects the food chain, all the way back to us. For us, why they are a problem for us, they can end up in our systems and release toxins, and they typically enter our systems through dermal abrasions, ingestion, and inhalation. How can you reduce the use of microplastics? Start using reusable water bottles. Stop smoking cigarettes. As I said, the filters in cigarettes are made out of plastic. Buy clothes that use natural materials. And try using zero waste products such as toothpaste that comes in jars, or toothpaste that are just chewable tabs that don't come in a plastic tube. You won't be creating waste. As of right now, scientists are identifying microplastics using attenuated tonal reflection ATR, and that is a sampling technique used in combination with infrared spectroscopy, which allows samples to be examined directly in the solid or liquid state without further preparation. And they're also using Fourier transformation infrared, which is FTIR, and that is a technique used to obtain an infrared spectrum of absorption or emission. One way they're removing microplastics is by using a bacteria called Pseudomonas, and it creates a bacterial biofilm. And with this bacteria, they create web-like nets, and they place it in the water, and then there it collects all the microplastics. It gets attached to the film, and then it sinks, which allows them to remove those microplastics from the water, and then they can recycle the plastics. What I'm doing currently is I'm identifying and quantifying microplastics in sediments. Those samples over there are the sediments that I tested. And I use Fenton's reagent, which is an iron 2 solution of hydrogen peroxide. And it helped separate the organic matter from the microplastic in the sediments. To conclude, microplastics are harmful. They will affect the food chain. They are toxic to us as well as fish and animals. There is currently work being done. As of right now, scientists are still working on ways to remove microplastics from the ocean to make it safer for us. And as I said earlier, there are ways you can help. Start using reusable water bottles, zero waste products, building with natural materials. And that's all. Any questions?
Any questions? Yeah, she's just beginning, that our undergrad is working with, lab. Yeah, they have classes, so still they're trying to do, a little bit research that helps for them to go to grad school. Any question about, no? Okay, so then, okay, next we will come to the, so I want our judges to put this one, as we student to the judges. Please judge the So our judges will do the judgment for high school. They work in the summer, so their parents are here. So let's see that how they will do that. Hopefully they'll have a good presentation. They really worked hard. So they are high school students. Let's see that Tasin Hussain is the first high school speaker. You can see that Tasin, you are in 11th grade. He's in 11th grader. So he just came in this summer, very hardworking. That gold nanoparticles, and they are using drug delivery. He'll talk about that. So judge, our 4 judges, so high school students are starting. So judge, and also we have a guest for Dr. Bay. Please judgment for us. So 5 of you are judges here for high school student judgment. Okay, you can go there or here. I'll help you. Okay. Oh, you wish it? Okay, you can come and then do that. Okay, start. Okay, Tasin, it's probably zero. Speak loudly.
Yeah. Hello, you guys hear me?
Yeah, you could take it out and then maybe speak loud.
Hello, my name is Tassin Hussain. I'm a junior at Western School of Technology and Environmental Science, and this is gold nanoparticles and their use in drug delivery. So today I'll be covering what are gold nanoparticles, gold nanoparticle synthesis, biomedical applications of gold nanoparticles, as you can see here, conjugation of gold nanoparticles with lipoic acid, and then I'll get into dye-sensitized solar cells, and I'll finish off with summary, future goals, acknowledgements, and references. What are gold nanoparticles? Gold nanoparticles are small gold particles with a diameter ranging from 1 to 100 nanometers. And one major difference between gold nanoparticles and normal gold particles is the color change. As you can see here, normal gold particles are yellow, while gold nanoparticles are wine reddish color. And this small size allows the gold nanoparticles to exhibit properties desirable in multiple fields of research, in my case, drug delivery. So why did I choose gold over something such as silver nanoparticles? Well, gold has a large surface to volume ratio and is also very malleable, so it can be shaped into things such as rods and spheres, and each one has a different purpose. And it also exhibits specific photothermal properties, which is desirable in detection of certain ions and tumors. And contrary to popular belief, it's actually not that toxic. And one article even claimed that gold nanoparticles are cheap, and it comes to about 25 cents per test. So to start off, I synthesized gold nanoparticles with the materials presented here. The main ones being gold chloride and sodium citrate. And I did 4 trials, but my most successful trial was trial number 3, where I applied a 1:6 ratio and used 0.8 millimoles of gold chloride and 0.48 millimoles of sodium citrate. As I ran the spectrophotometer, which is a machine used to test how much something absorbs, I got an SPR, surface plasmon resonance, of about 526 nanometers, which is a key trait of gold nanoparticles. And my absorbance was pretty high, but I applied a 1/3 dilution to get it under 1. And my mean size was around 16.5, which is desirable. So to get into further use, I went into biomedical applications. There are some such as targeting nucleic acid delivery, but the main one that I focused on was drug delivery because many lives are taken due to cancer and tumors. And in 2021, 1.9 million new cases will occur. And gold nanoparticles has a power to change this because it plays an important role in endocellular disease therapy. Due to its great biocompatibility, small size and low toxicity, and evasion of multiple drug resistance, which is a key trait of tumors. So to move forward with my drug delivery, I conjugated lipoic acid with gold nanoparticles. And as you can see here, this is dioptic acid, and it's also known as lipoic acid or alpha lipoic acid. This is used as an antioxidant, which is usually ingested or injected in the bloodstream. But with the use of gold nanoparticles, it can be used directly to remedy the effects of arrhythmia and other problems as it affects the organs in the bloodstream. So the gold nanoparticle trial that I used was a recreation of my best trial where I applied a 1:6 ratio and again used a 0.8 millimoles of gold chloride and 0.48 millimoles of sodium citrate. I got again a surface plasmon resonance of about 526, but this time I couldn't get around the same size. I got around 25.4 instead of 16.5, but it's still usable. After combining lipoic acid with the gold nanoparticles, I got this graph from the spectrophotometer, and the screen is blocked, but the surface plasmon resonance went from 526 to 536, which shows that the lipoic acid and gold nanoparticles has properly combined. Unfortunately, at this stage, we came across some problems acquiring some drugs such as bleomycin and doxorubicin to take this to the next level and actually inject into tumors and test if it works. So I switched my focus and went into dye-sensitized solar cells to align myself with the theme of this STEM night, which is power. To familiarize myself with dye-sensitized solar cells, I created various dye from vegetables. The one I used was red pepper, and the reason I wanted to do this is because it is an efficient alternative to normal silicon solar cells, and it's also environmentally friendly and cost effective. As you can see here, the diagram of the DSSC, light goes in and reacts with the dye, which is the anode side, and then it goes from a ground state to an excited state. At this stage, it can power something, and when it goes to the cathode side, it reduces and gets the electron back, and this cycle repeats itself. And the vegetable that I focused on was obviously red pepper. So after creating the slides with titanium dioxide, dye, and graphite, I ran a solar simulator and I got an efficiency of about 0.1. This is not desirable, but it provided me a basis to work off of in the near future, and I hope to work on it and maybe present next year. And my time here was important because it allowed me to familiarize myself with everything done in the nanotechnology lab, from synthesis of gold nanoparticles, conjugation of lipoic acid, to dye-sensitized solar cells. The future goals I have, I just want to leave this facility with enough knowledge to one day come back and continue my research from where I left off of and eventually publish a paper, which will help me get places in life. And I'd just like to say a special thank you to Dr. Gan, Dr. Dean, and the faculty at Coffin. And thank you guys for listening to my presentation.
Okay, so Levin gave a passing sign, wonderful presentation, and really he worked hard in the summer. So do you have any question for him? Yes, Dr.
Very
Shabbat.
nice presentation, very good job. I mean, why in one of the slides say that it is a thermal therapy?
Yeah, go to that
Yes.
that
Oh, more.
no,
Yeah.
for the thermotherapy.
So you can also use it for detection of lead ions, which we were working on, but we didn't get to finish it due to school starting.
Okay, but why no photodynamic?
I think I actually don't know because I haven't researched it enough, but I think the heat plays a important factor in the gold nanoparticles.
Okay.
Right, that is the answer he's asking for.
Yes.
Good. So what part you did that here?
I worked on drug delivery
And
also detection of lead ions.
lead ions, okay? So two part he's did.
Last question.
Yes.
Why the selection of the red pepper?
Oh, red pepper. I just like the smell of it. I'll document it.
Okay.
Okay, Tolu, please.
Yeah, I don't have a word that it's a very good presentation.
Yeah.
So, well done, like, very good slide as well. Some people are indicating on line that you have.
Oh,
Yeah.
really? Okay, go ahead. Ask, somebody is asking question. Yeah, please unmute and then have question. Anybody want to ask? Hello, are you hearing me? Anybody? Anybody want to ask from there? Somebody virtually? Some have questions. I don't know. Okay, maybe later we can talk. I don't know. The chat box. See that.
Well, you can write it down.
Yeah, I think it's chat box. Go to the chat box. Yeah. But it's okay. The chat box, is there any question?
Yeah.
That, see that. No, I didn't see any question. I'm sorry, I can't hear. Can you hear us, everybody? No.
Online?
Those who are online, can you hear me? Okay.
Yeah, she
Yeah, so
Yes, we can hear you.
okay, you can hear me? Okay, good, good. Is there anybody have question?
Yes.
But it's okay. Because of time restriction, we need to go. Okay, thank you so much, Tasim, for your nice presentation. Yeah, you have a question?
Yeah.
Okay, Tasim, last question, okay.
So first of all, I wanted to comment on the clarity of your presentation. Really, really good presentation. Do you have any reasons to speculate why there's variations between your test treated at the best sample, but then when they're ready to use the why couldn't you do
One major problem was actually the storage. So after some time, I let it sit for about 3 days. So if the particle is aggregated, so next time I can probably store it better in a cooler temperature, which can remedy this and keep that as one size.
So when when you're doing experiments, I try to reduce variation as much as possible.
Okay, thank you, Rital. Good job. Our next high school presenter, Rital, are you in 11th grade?
12th grade.
12th grader. He's a senior, okay? Rital, very good job. You did, yeah, really 3 or 4 students came to this summer. They worked hard. This is the Rital presentation. He will talk about the silver nanoparticle synthesis for antibacterial application. Rital, 12th grader.
So,
Go ahead. Speak
hello.
loudly.
So, hello everyone. My name is Bertal Saha. I'm a senior at Urbana High School. This summer I worked in the nanotechnology lab here in Coffin State and under Dr. Rudin and Dr. Gan. And this is my project on silver nanoparticle synthesis and their antibacterial applications. So for my outline, I'll be discussing some background, some applications, my synthesis methods and characterization, the antibacterial experiment that I did, work I did with the dye-sensitized solar cells, and I will finish off with conclusions, acknowledgements, etc. So first, what are silver nanoparticles? Silver nanoparticles are silver particles with a diameter of 1 to 100 nanometers. They have a wide range of applications in medicine, cosmetics, electronics, and more. They come in various shapes, such as spherical, rod, and triangle. And they display usually a yellowish color. This is due to them being efficient at absorbing and scattering light. They also have a high dielectric constant that causes them to absorb light in the visible region. And the wavelength of this absorbance corresponds to what we call the color yellow. So the purpose of this project was to synthesize different silver nanoparticles using the chemical reduction method and use them to effectively kill bacteria. And so for this first synthesis method, I use silver nitrate, and for reducing agents, I use trisodium citrate dihydrate and tannic acid. And so to make these nanoparticles, it involves making solutions of these different chemicals, and you would mix them together and heat them up on the hot plate, and that would result in the nanoparticles. And you can see here, this is my sample. You can see the yellowish color due to, as explained before. And so for characterization, I use 2 different techniques, the UV spectrophotometer and the dynamic light scattering DLS. So the UV measures the absorbance and the wavelength, and I got an absorbance of 0.437 at a wavelength of 408 nanometers, which is consistent with the wavelength silver nanoparticles should be. It should be around 400 to 410. Dynamic light scattering is for measuring particle size, and I obtained a particle size of 18.6 nanometers with a standard deviation of 7.4, which is pretty small, but the goal is to get as small as we possibly can, such as like 10 nanometers or smaller. For my second synthesis method, it's similar to the first method, except no tannic acid was used. And we have to mix these solutions again and heat them up on the hot plate. And these are my samples. In the beginning, when using the UV, I obtained a wavelength of 414, which is fine, but the absorbance was 1.496, which is a bit high, greater than 1, which indicates the sample is too concentrated. And to correct this, I did a 1:3 dilution, which was able to bring the absorbance down to 0.481, you can see, and then the wavelength did not change that much. And for my DLS results, I obtained a mean particle size of 39.9 nanometers, which is with a standard deviation of 14.6. This is an increase in particle size compared to the last sample. However, it's not too big, it's a medium size that we would like. For my third method, I used a different reducing agent, sodium borohydride, with a 4 to 25 mil ratio of silver nitrate to NaBH4. And the difference with this method is you had to chill the solutions in ice because sodium borohydride is very reactive, so no heating was involved. I obtained a wavelength of 394 nanometers at absorbance 0.566, with a mean particle size of 18.9 with standard deviation of 6.9, which is another small size comparable to the size obtained from the first method. And this is just a summary of my characterization. You can see the max absorbance, the wavelength where that maximum absorbance happened, and the mean particle size. And so, as said before, there are many applications of silver nanoparticles, especially in the medical field. Some of these include antiviral, anti-tumor, antifungal, and the one I focused on, which is antibacterial applications. And this is a potential antibacterial mechanism. And so what happens here is silver nanoparticles will adhere to the bacterial cell membrane. And when they do that, they release silver ions through oxidation. You get an attraction between those positive silver ions and the negatively charged membrane. And this disrupts the structure of the cell membrane, leading to increased permeability. And this causes an increase in silver ion uptake. And what happens with this increased silver ion uptake is various things, such as deactivation of respiratory enzymes, interruption of ATP production due to the production of reactive oxygen species. The silver ions also interact with the sulfur and phosphorus on DNA, which disrupts DNA replication. And they denature ribosomes, which inhibits protein synthesis. And this is a graphic that summarizes this mechanism. You can see the silver nanoparticles releasing ions to the membrane, disrupting it, increasing permeability. The ribosomes here are denatured to stop protein synthesis. There's interaction with the DNA to stop replication, and silver nanoparticles perforate through the membrane here. And so this is my antibacterial experiment that I did. The goal was to test my 3 silver nanoparticle samples on E. coli bacteria. And some background on E. coli is it grows at 37 degrees Celsius with a generation time between 20 to 30 minutes. And so first I cultured E. coli in my liquid medium, and after a day I transferred to a nutrient agar plate. I divided this plate into 3 sections, a control, 5 microliter and 10 microliter. And the control, I just put 5 microliter of water. And then I transferred 5 microliter and 10 microliter of my silver nanoparticles to their respective sections. And I put in an incubator for them. So here are my results so far. For my sample with TSC and tannic acid, I was able to find an area of inhibition. You can see it right here and zoomed in at 5 microliter. And so this lighter area right here, that's the area of inhibition where there's no bacterial growth happening. And then for my sample with just trisodium citrate dihydrate, there was also an area of inhibition found. And for sodium borohydrate, there was none found. And then, so zooming in, this is the area of inhibition found with my TSC sample. I also did work with dye-sensitized solar cells, and the goal was to develop solar cells with vegetable dye and a counter-electrode. So to do this, I made a white paste for one of the slides using titanium dioxide, acetic acid, and soap water. I put beetroot dye on this white side, and on a second side, I put a counter-electrode. And then I clip those slides together, add an electrolyte to get the final solar cell and measure the efficiency. And so this is the paste I made. These are the painted slides on a hot plate. And then this is the final solar cell where, see this slide right here, has the purple color, that's the beetroot dye. And this black slide is the counter electrode. These were my results obtained. So I have the Nyquist graph, which measures the resistance. This is the frequency versus degrees graph. And this is the voltage versus current graph. And I obtained an efficiency of 0.066, which could be better, but there are some limitations as to how I did the experiment that could have caused this. One future project that could be done is to make a solar cell that instead of using counter electrode, you could use silver nanoparticles, and the belief is that the efficiency should increase due to the silver nanoparticles in the solar cell. And so from my conclusions, I can conclude that silver nanoparticles with trisodium citrate or trisodium citrate and tannic acid can cause an antibacterial effect on E. coli, but particles with sodium borohydride cannot, and more trials will be needed for further data. I'd like to acknowledge Dr. Udine for providing me the opportunity to work here, Dr. Ghan for providing guidance and help throughout this internship, and Dr. Dominique Dotson for help with the bacterial culture and antibacterial experiment. Thank you. Thank you very much.
Wonderful. Just think about that. 11 grader, 12 grader. They did good job, huh? Again, please clap. Okay, any question for Rita? Yes.
I see that in one slide you show that
Sure.
the resistance of stopping the
Yes.
your bacterial growth after applying the silver nanoparticle.
Right.
And is there any comparison, like right now the medicine or antibacterial medicines and the silver nanoparticle particle? What is the comparison? Like this has more effectiveness, or
Based on what I see from their inhibition, there could be more effectiveness because you only have this region right here where there's an area of inhibition. Perhaps using different samples could create more areas of inhibition in the bacteria.
Okay, any question? Well, if not, then thank you so much, Rita. Good job. So we'll continue for our high school student, and then we'll be back down the grad, and then finally we'll end up with our graduate student presentation. Next presenter is Afrin Reza. Afrin, Rita, Tasin, Noor, they worked really hard this summer. And I really thank you for their parents. They came for so far away to work in our center. So hopefully undergrad students and high school students, they work together with the grad students. Like, it's a nice combination, as you know that. So we are trying to do this kind of work for our students, high school to all the way grad student. Okay, Afrin is what grade? 11th grader. Okay, Afrin is 11th grader, and yes, that's the high school name. You can see that gold nanoparticles in drug delivery. She will talk about that. Afrin, floor is yours. Okay.
Hi, my name is Afrin Reza. I'm an 11th grader at Thomas S. Wooten High School. And what I focused on this summer was gold nanoparticles in drug delivery. So what I'll be going through today are what are gold nanoparticles, why gold, the application of gold nanoparticles, dye-sensitized solar cells, drug delivery, gold nanoparticle synthesis, gold nanoparticles and thioptic acid, my conclusion, acknowledgements, and references. So what are nanoparticles? Nanoparticles are obviously from the name very small particles, and because of their minuscule size, they have a very large surface area to volume ratio compared to particles of a larger size. They range from 1 to 100 nanometers, and compared to a normal meter, it would be 1 times 10 to the negative 9. Their small size allows them to possess unique optical, chemical, and physical properties. For example, bulk gold has a melting point at 1064 degrees Celsius, but gold nanoparticles of 2.5 nanometers will have a melting point at 300 degrees Celsius. That kind of just demonstrates how much they differ by size. So here's a visual for you to kind of imagine how small a nanomaterial is. So nanomaterials are here, 10 times 10 to the 9 meters, and you can compare it to a red blood cell and a virus, and see how small it is. So why did I choose gold? The ligand gold bonding outside a human cell is high because of the concentrations of glutathione in a human cell. Glutathione is an antioxidant found in all animal cells, It's made up of amino acids, and it's capable of preventing damage to important cellular components caused by reactive oxygen species or free radicals. So glutathione, the kind of molecular structure of it is one amino group, which is NH2, and then a carboxyl group, which is COOH, and the amino group is basic, the carboxyl group is acidic, and they kind of balance each other. And then there's the rest of the molecule based on the structure of the amino acid. So there are two ligand sites within the glutathione, which makes it kind of good to bond ligand and gold nanoparticles to it. One is located in the N-terminal, and one is located in the C-terminal, which is the amino group and the carboxyl group of the cell, of the amino acid. There's also photothermal and absorbance properties. So gold has a very high absorptivity, which is really good for chemotherapy, because a big problem with chemotherapy is that when they put the radiation onto the tumor cells, it will affect the cells or the healthy cells around it, and it'll end up creating more cancer. So gold is really good for that because it's very target specific. There are many applications of gold nanoparticles that you can see here, and what I focused on was drug delivery, but I also did, as everyone did here, dye-sensitized solar cells, or DSSC. So the ingredients for the dye-sensitized solar cells were mainly the acetic acid, soap water, FTO slides, titanium dioxide, and ethanol. So the purpose of using organic solar cells compared to silicon solar cells is because of its high conversion efficiency. It's low cost and environmentally friendly. Although I didn't do solar cells with nanoparticles, solar cells can be done with nanoparticles, and they have 147% improved efficiency rate compared to a normal silicon solar cell. It's because of their plasmonic effect and resonance enhancement, which is when particles whose electron density can couple with electromagnetic radiation of wavelengths. So I can kind of explain how the solar cell works, even though everyone else already did. There's an anode and a cathode, and there's an electrolyte, which in this case we used iodine, which will go in between the slides. And the electrons will transport from the anode to the cathode, and that will generate electricity. These are the FTO slides that I used with titanium dioxide. They're kind of drying on the plate because they need to dry before we can put the dye on them. And this is the completed solar cell. You can kind of see the two cells. The kind of yellowish liquid in the middle is the iodine, and the black is graphite. It's really hard to see, but the back portion is the red pepper dye. So what I focused on here was drug delivery. So as you all know, cancer is caused by mutations in the cells, in the DNA, either through genetics or environmental factors that causes unrestricted cell division, which is why it spreads so quickly and why it can be so deadly. So there's always a need for better treatments, and in the future, more treatments. So since nanotechnology became like a growing field, many scientists have been looking into nanomaterials to combat the cancer crisis. So this is because nanomaterials are extremely small, so they're biocompatible, and they can interact with some cellular components that can be undetected by white blood cells or antibodies that kind of want to save your body, but by doing so, they might expel things that might help you, which is a problem with your standard drug delivery. Your bodies or your doctors are trying to put the drug into your bloodstream, but your body doesn't know that, so it kind of kicks them out. But with nanomaterials and nanocarriers, it's so small that your body can't detect it, and it will help you. So that's why it's an ideal tool for modern medicine. So there are two ways to deliver drugs through nanocarriers. There's passive targeting and active targeting. So you can physically or chemically bind the drug to its nanocarrier, and The thiol groups on the surface of the nanoparticle will ensure steady release through the glutathione, which I explained earlier, and the glutathione will place the conjugated molecules on the surface of the nanoparticle. And using controlled light and radiation during chemotherapy or spatial temporal regulation, you can kind of control which, like, directly to the tumor instead of affecting your normal cells, which you can see here in this diagram. It doesn't, the targeting ligand and drug substance won't bind to your normal cells. However, it will bind to your cancer cells that need to be treated. So what I did here this summer was gold nanoparticle synthesis. So the main ingredients were gold chloride and sodium citrate. So first, I created a 0.8 molar gold stock solution using gold chloride, and then I created a 0.48 millimolar solution of sodium citrates, and I placed this solution on a hot plate with a stir rod, and the nanoparticle solution is ready when it becomes a dark red color. There are two instruments I use for characterization. One of them is a DLS, or a dynamic light scattering, and this is used to measure and analyze particle sizes ranging from 1 nanometers to 6 micrometers. I also use the spectrophotometer, which is used to measure how much light a chemical substance can absorb. So this was our best trial, which is a 1:6 ratio of gold nanoparticles to sodium citrate, so 0.8 to 0.48. So this is, I guess it got cut off, but the absorbance at 524 nanometers when it was a 3:1 ratio of water to gold nanoparticle was about 0.99, which is a very desirable absorbance. Our DLS was a 25.4 nanometers, which isn't the most perfect size for a nanoparticle that you want to use for drug delivery. That range should be from like 1 to 15, but it's still usable for experimental purposes. So I also binded gold nanoparticles to thioctic acid or lipoic acid. So you kind of just determine how many ligands, which in this case was the thioctic acid, could fit onto the surface area of a gold nanoparticle. You use sodium hydroxide and measure the pH to kind of mix the two together, and you get your gold nanoparticle solutions that's binded to thioctic acid. So you can see the SPR difference. This red line is the normal gold nanoparticle, which is around like 5 to 10. And the gold nanoparticle with thioctic acid, which is represented by the green line, has a slightly higher surface plasmon resonance than the normal gold nanoparticle. So the purpose of the thioctic acid is because it mainly depends on the glutathione concentration inside your tumor cells. Not your tumor cells, the tumor cells. So the disulfide bonds between the two cytosine residues, which is an amino acid in your cells, it stabilizes proteins by maintaining that covalent bond, and that's it stabilizes harsh oxidizing environments within cancer cells, and cancer cells need more protein synthesis, obviously, because I explained there's a constant repetition of like growing cancer cells, and so that disulfide bond is something that's constantly forming, and the goal is to break that disulfide bond, which is disulfide bond cleavage, and you use polymeric drug carriers or polymeric nano drug carriers, and this will release more of that anti-cancer drug, and something called a cross-linking sperm will prevent premature drug release until it reaches the tumor site, and the disulfide cross-linked polymers from the thioctic acid will form a ring structure and kind of slow down the replication of the cancer cells. So in this diagram, it's docetaxel and how docetaxel can attach itself to the gold nanoparticle, which can then be brought into the tumor cell through the bloodstream. So in conclusion, this summer I was able to participate in a variety of experiments, DSSC, gold nanoparticle synthesis, target drug delivery. I also did detection, which I didn't want to speak about, but there's a very bright and prosperous field in the prosperous future in the nanoparticle field, especially in the biomedical applications. I'd like to acknowledge Dr. Gan and Dr. Udine for giving me this opportunity this summer, and I hope to continue my research over the school year and hopefully publish a paper.
Thank you so much, Afrin. So you see that how this actually one more high school student we are done, and I know that it will be difficult for our judges to judge, but let's see that how it goes. Okay, Afrin, you did good job. Any question for Afrin? Anybody? No question? And that means Afrin did good? Okay, thank you. Thank you so much, Afrin. Good job.
Hello guys, my name is Nuruddin Fargali. I'm still a student in Mount Hebron High School. So I will start first with some information about myself, and then with introduction about silver nanoparticles, and then the synthesis, and I will go with the characterization, and then I will show you what I did with the silver nanoparticles and the E. coli bacteria, and then I will go to my conclusion. So currently I'm 16 years old, still a student in Mount Hebron, a junior. I'm planning to finish my high school years this year. I'm planning to finish my high school in 2022. So silver nanoparticles are nanoparticles of silver that has a size from 1 to 100 nanometers. It is used in many fields, especially in drugs for drug making. Silver nanoparticles do have a toxic effect on any cell, which will cause it to be trapped in a specific area. My work with silver nanoparticles, mainly I'm putting it with drug making for cancer. So I have used for here are what I used: silver nitrate 0.100 1,202 grams plus 100 milliliters of water, and I took from it 50 milliliters. And as for the fact, we used distilled water at that time, and I did the same thing for here. I don't know which section. So I went to heat the silver nitrate alone for 20 minutes, and then heat and stir the sodium citrate and the tannic acid together for 20 minutes. After that, I will start mixing everything together and stirring and heating everything for like 5 minutes. After that, I should let my silver nanoparticles go for cooling. That is okay. So this is my silver nanoparticles right here. When I made it, it looks like sort of red. And this how it did look like after 2 days. So in the beginning, I did use the spectrophotometer, which is this, and the DLS, dynamic light scattering, to measure in the beginning here the absorbance and the length of the silver nanoparticles in nanometers. So this in the beginning was my first trial. I got 420 as my as for my wavelength, and the absorbance was 1.028, and the length was 70.3 nanometers. So in the beginning here, as you guys can see, it seems to be having 2 peaks, and it seems to be like over 1. My plan is to at least get it from 0.9 to 1 for my absorbance. So in that day, I took half of my sample here and added water. and so I added 1 milliliter and 15 microliters of water, and it seems to be like it went down after that. So after 2 days, I got, it seems like the 2 peaks that I have got in the beginning, one of them was removed, and the absorbance rate went down a little bit, and that amount seems to be like the amount that I wanted and needed for the absorbance. And also, I also see like there's a problem that my silver nanoparticles would require at least a day or 2 if I want to be like using it for cancer treatment. So I have used my silver nanoparticles with the E. coli bacteria, and they are usually found in the digestive system, and they do help the body to digest the food. They are harmless. So I started to take the bacteria close to an open fire just to like keep other bacteria in the air away from it. And I took it into liquid medium to culture it and make it grow and spread more for at least 1 day. And then I added the E. coli bacteria to leave it for 1 day. After that, I did put it on agar plates, and I added silver nanoparticles on it. And so I had to leave it for like a whole day in order for me to see the results on it. So as this is where like if we were getting the fire from, I had to keep my hands too close to it to keep the other bacteria in the air away from it. And here we did put our E. coli bacteria. As for those 2, those were all silver nanoparticles. This one was made on the 2nd of July, and this one was made on the 15th of July. So here, as you can see, I have made 2 agar plates. On this side here, you see that there is a word control. We did just put in it water, so we can see the E. coli bacteria spreading around. As for the other sides here, those 3, we did put silver nanoparticles, but we did put in a different amount, like here 5 microliters, 10 microliters, and 15 microliters. And we did the same also for this one, but our research is still to be continued for this. And as you can see here, we still like see a little bit of effect here. Like you see a little part where there's like where there seems to be some bacteria trapped here. So my silver nanoparticles problem is that it can be just used for like after 1 day or 2, which is something that I have to make up since I will need to lower the amount of components either in the silver nitrate or the sodium citrate or the tannic acid. So my problem with the silver nanoparticles also, which is related to the components that I have used, that it's a little bit concentrated because as I said before, I need the absorbance height from 0.9 to 1. I thank Dr. Rudin. He was the person who gave me the chance to be here. And I thank my mom a lot. She was helping me. She was helping me, taking me here every day, wasting her time. I thank Chica and Dr. Gan. They were both of them helping me, even though like sometimes I didn't understand. I was asking too much questions. And I want to end my presentation here with thanking you guys for coming here and listening to my presentation.
Okay, so thank you, Noor. So there we have 40 students. We have actually more, but especially these 40 students worked really hard. Just really thanks to their parents as well. So our judges are in the meantime when we finish with our undergrad and grad. So I need your judgment, and Dr. Nesbitt will lead that position, first, second, third, fourth, according to our judges. Okay, so now I know that it's really tough to stay, but due to the time restriction, because we would like to finish and then we go to the lunch. That is our plan. So it's a, please, I know that it's a long time, but for our students' benefit, let's have patience and continue. Okay, so next is Ruth. We'll talk about that. She come back. I don't know what happened in that time. She now maybe was nervous or not. She's okay right now. Okay, so Ruth, go ahead.
Good morning. My name is Ruth Domoa, and I'm a junior here at Coffin State University. I'm a biology major with a minor in chemistry.
You're going to talk over there. Yeah.
Yes, so my presentation is on nanotechnology and gold nanoparticles. My presentation will mostly focus on the synthesis and application. So nanotechnology is the study, synthesis, and application and characterization of matter on a nanometer scale. It is important for different cosmetic, food, industrial, and medicinal purposes. So gold nanoparticles, as I said, they're used in numerous applications, and their size is 1 to 100 nanometers in diameter. Okay, so I did have a video explaining more about how they can be used in research and science, but it's not plain. So. I was introduced to this research by Dr. Udine when I took his Chemistry 101 class. He said that would be a good experience and it'll be important for our resumes, and he said he would give us a stipend. So, of course, money's always a bonus. So in the lab, I'm under the direction of Dr. Gan, and he started off by introducing me to numerous different research topics. He started off with the dye-sensitized solar cells. I did a few Jamun dye cells. He also showed me water testing, chromatography, and then finally the gold salt solutions. I decided to continue the gold salt nanoparticles because of their importance in cancer research and how it can create different medicines and treatments. I also have an aunt that died from stage 4 cancer in about, it was March, so that also made me more interested in it. I created my gold nanoparticles using gold salt and sodium citrate as a reducing agent. Sodium citrate is important as a reducing agent because it prevents the gold nanoparticles from coagulating when they go through the colloidal process, and that is when the particles will form to bond together and then they'll get too big. For my gold nanoparticles, Dr. Gan already had the gold salt solution, so I didn't have to synthesize that myself. And then I made this sodium citrate solution by using 5% sodium citrate and 10 milliliters of water to dissolve it in. So I take the sodium citrate and I pour it to the gold salt solution as it stirs and heats up on a stirrer. And then when it begins to boil, I take it off and it cools down. So I have videos. So this video just shows me pouring the sodium citrate to the goods. And then as you see, the color changes from about gold and it starts to get. And this video shows the color change as it continues. So this picture is of one of the gold nanoparticles, but this this mixture was too concentrated, so I had to further dilute it. And then this is how I dilute it. I just continue to add more water to the the flax so it could get like lighter in color. This photo shows some of the gold flakes on top of it. I had to drain it, so filter it, so those wouldn't be in like the final mixture at the end. So future applications that I would use would be in for like cosmetics. It could help with like hyperpigmentation. Because I did more research and I saw that there are some things that sell for like $420 using gold nanoparticles in them. And then more applications would be to figure out how it can help women with infertility and childbirth problems, and also for Alzheimer's research. And I'd just like to thank Dr. Udine and Dr. Gan and the Center of Nanotechnology for allowing me to be able to research.
Okay, thank you, Ruth. Okay, so mainly you see that the two types of work in this center, the high school and undergrad, they are working on dye-sensitized solar cell and then nanoparticles like gold and silver. And then the work is still going on. So we'll do that. They'll come back time to time after the school. So until we get a good publication as our goal. And then we did before. A lot of high school students are in the manuscript and would like to see, and I'm sure that they will. Okay, so now next is Coulomb. Actually, Coulomb, Chica, Baldwin, Beatrice, Nina, they took chemistry actually last semester. So they are working still for a few semesters, and I'm pretty sure they're good at their research skill that I see them. So I hope they continue to work all these 4 years to have more work than will continue to write research article. Okay, Coulomb, go ahead.
All right. Good morning, everyone. My name is Coulomb Nagata, and I will be presenting on dye-sensitized solar cells. Okay, so fossil fuels are the resource that we use a lot. Currently, I think we use it about 85% of our resources that we currently use are fossil fuels. And fossil fuels are made from dead organisms that release energy through combustion. Most deaths by air pollution were caused by fossil fuels because burning fossil fuels releases a bunch of carbon dioxide, and carbon dioxide can lead to things such as global warming. I'm sorry. And the thing about fossil fuels is the fact that they are non-renewable. So we are currently looking for a replacement to replace the fossil fuels because they're non-renewable and they're actually very toxic to the environment. Due to the fact that the population is increasing and there's demand for developing countries, people have been looking for new methods, and we've come across dye-sensitized solar cells. So we're currently using the sun because it is a renewable resource that has been around for billions of years. People have been harnessing solar power as early as the 7th century before Christ BC. There have been recordings of people using magnifying glasses to concentrate the sunlight on wood so that it can catch fire. So dye-sensitized solar cells belong to a group of thin film solar cells, and they have been under extensive research for about 2 decades. And all dye-sensitized solar cells contain coated transparent conductive oxides, a semiconductor film, and we use titanium dioxide because it's cheap and abundant. We also use a sensitizer that absorbs on top of the semiconductor, an electrolyte, and an electrode. Okay, so dyes are important in dye-sensitized solar cells because they're effective for turning photons, which are the particles from the sunlight, into electrons. And it's common for people who do dye-sensitized solar cells to use ruthenium, and these dyes are metal-free. So some pros and cons of dye-sensitized solar cells is that it's low cost. It's very simple to prepare. It's not as toxic as coal and other non-renewable resources, and it's very easy to produce. The con is that you can't use it to its full efficiency. It's only about 12% efficient. And the most efficient version of the dye-sensitized solar cell is the silicone one, and it reaches about 20 to 30% of efficiency. So for my procedures, I would get some titanium dioxide, some soap, water, glycosides, and acetic acid. And I make the paste, and I use the formula of like 2.4 grams of titanium dioxide powder, 10 millimeters of water, and then 1 millimeter of soap water. And then, of course, you have to check the conductivity of your glass slide using a multimeter. And with the conductive side up, you will apply a dab of titanium dioxide paste. You will use a spin coater to evenly coat the plate, and then you'll put it on heat to let it dry, and you let it cool down, and then you'll add whatever dye you would prefer to use. And here's a picture of a dye-sensitized solar cell. I'm currently researching this. I haven't been able to get some good data, so hopefully by next year this time I'll have data to present to you guys. Thank you for listening to my presentation. I would like to thank Dr. Vaughn and Professor Dean for helping me with my research.
Okay, thank you, Kulam, for your, I know that you'll, okay, let's clap her. I know that she just actually, as she said, you are still working, and hopefully you will accumulating more data in future. Okay, thank you. Okay, next is Mariam is our just a freshman. She just entered freshman, came from high school. She's our undergrad student here in biology, so she'll talk. And her brother is Noor, already presented, and hopefully he will come to Coffin too, you know. So let's see. And her mom, their mom is working hard, believe me. So I really respect all of parents are here, those who work for their kids. Really, really amazing. Okay, so Mariam will talk about again. So our, as I told you, that they're learning to how to make the DSC, dye-sensitive solar cell, and its application, and also nanomaterials, as you see, the silver and gold. And you know that they're undergrad and high school student, and I think they're doing very good. Of course, the judgment is yours. I'm not tell that. That's why professors are judging them. Okay, Mariam, please go ahead. Take it out, and then your mask talk.
Good morning, everyone. My name is Mariam. Like Dr. Dean said, I'm a first year student here at Coffin University, and I major in biology. Today I'm going to talk about the fabrication mechanism and advantages of using dye-sensitized solar cells. So basically today I'm going to talk in this presentation about the fabrication process and the results and the conclusion. So what are dye-sensitized solar cells? They are composed of a layer of titanium dioxide and covered with a dye that absorbs visible light and converts it to electricity. The SSCs work as a low-cost alternative to super solar cells. So basically, when a light source meets them, the electrons store the energy. The energy is then transmitted through the semiconductor, which is the titanium dioxide paste. So their advantages are they offer both flexibility and transparency. I'm sorry, give me a second.
It's okay. Take your time. Okay? Good.
They're also transparent, making them suitable for window application. They're really affordable and easy to produce. They also have a low toxicity level. To make them, I started by making the titanium dioxide paste. I also used red cabbage and pomegranate dye. And how to make the pastes? I used 1.2 gram of titanium dioxide, and 5 milliliters of acetic acid and 0.5 milliliters of soup water. So after checking the conductive side of the slides, I secure the slide on the spin coater and spin a coating of the pastes. After that, I place them on the hot plate to dry, and then I put them in the petri dish to dye them and leave them overnight. After that, the analysis process is basically I start by getting other slides, plating them with a layer of graphites. I put them in the solar simulator with the side part facing the lights. So these are the results. As you can see, basically the pomegranate dye is more efficient. Like the results are basically similar, but not similar. They're close, but the pomegranate in general is better. In conclusion, the pomegranate is better than the cabbage dye. And I'll just end this by thanking Dr. D and Dr. again. It's obviously my
Okay, no problem. You tried. Thank you. No problem. She's a little bit shy, but you're doing good. So don't worry. Okay, so we are done with the undergrad and high school students, and there our judges are judging for high school student only. You did good job. Okay. See, her mom is hugging her. That's a good thing. Okay, now our grad student, 2 more, then we're done, and then we'll go for lunch. And thank you so much, those who are in virtually for a long time to stay with us. Still, we have a lot of people out there. So what I want to do is that encourage our kids to have a future scientist and to work in the lab and get the hands-on experience. This is very important. That is, we are trying to do that all these years. Okay, now, Jiru, or Samson wanted to start. Okay, Samson is virtually, he will present from Morgan. Okay, Samson, you can start your presentation. Okay? Samson, can you hear us?
Yes, I can hear you.
Good, good. Okay, Samson is a PhD. Samson, can you tell about you first? What's your status right now at Morgan? I know that you are PhD candidate or PhD student. Tell us about and then start your presentation, please.
So my name is Samson. Thank you for having me in this conference. It's a great conference, a lot of learning. Again, my name is Samson, a PhD student here at Morgan State University. And today I'll be presenting to you some of the work that I've done in collaboration with Coffin State University. Can I be allowed to share my screen?
You can share, yeah, you can share your screen, please. So Samson is working with our group, our center, with his boss, Dr. Sitter. So we are working last couple of years, and we have a couple of publications already we published. So that's a good thing. This is a good collaboration research with the sister institution.
Maybe we have to accept the share the image.
Okay, I see.
She's a presenter.
He's a presenter. He's supposed to share. Is it okay?
Seems I'm having a problem to sharing my PowerPoint slide.
What problem? What is the problem? But you're the presenter. I don't know that. Is there anything it shows that you cannot share? Do you want to call Katie? And in the meantime, Tolu can present. Samson.
Yes.
Maybe let's help you with calling IT person.
Okay.
And then in the meantime, Tolu can talk. Okay.
Okay, sure.
Thank you so much. Okay, Tolu, you can come and then you can call Kelly that what's going on. Okay, Tolu, please, you can present your presentation, then bring our presentation. So Tolu is also working with Dr. Abibi from Morgan State. So she's a PhD student there. So as I told you that I will be her co-advisor as well as Morgan side will be Dr. Abibi. So we are doing like in the last couple of years, we are bringing this kind of graduate student to work with our research center. As you know, our research center is very much good apparatus and equipment, highly equipped. So they are interested to work with us collaboratively. So we are actually going to submit a paper by Toe's name with our both Coffin and Morgan. So hopefully we'll publish soon her work. Okay, go ahead. Tolu.
Hi, everyone.
Speak loudly, Tolu. Okay.
Hi, everyone. My research actually is between Morgan State University and I'm doing an application in Coffin State University. So basically, I met Dr. Eugene like 2 years ago during a conference like this, and I presented my work there, and there is need for me to do application. So the most why I met him, and it's actually a very good thing because there's no point doing research without an application. So thank you, Dr. Eugene, for the opportunity, and I really appreciate it. So I'm a bioenvironmental science student in Morgan State University, and this is my third year in the doctoral program. And my professor's name is Dr. Abibi. And the goal of my research is that the goal of my research is to improve human health by studying soil environmental toxins and identifying them and how we can detect those toxins and also reduce the effects on human health. So I'm working on over 20 samples, and I just selected a few that I'm going to talk about. And I will talk about the synthesis, the studies of photophysical properties on the rhodamine dyes and their method complexities and the application in dyes and size of the cell. Also, before I move forward, I'm also looking at some areas which I would love to do application. I love to do application in cell. So I don't know if I can get people to work with, and also in water. That would be a great place to do application as well. So the background, rhodamine dyes have been used for so many years by different scientists, and this dye have been so helpful in detecting environmental toxins and also in detecting environmental heavy metals in the environment, so as to be able to reduce these effects on human health. So this is the color of the rhodamine dye I'm working with. I'm working with a 6G compound, and this is like their base or base structure of all these rhodamine dyes. They are anthocyanins, and the popular one that I use is rhodamine B and rhodamine 6G. And also I attach up to more than 20 derivatives to this rhodamine 6G because they are so good in detecting of mercury, copper, iron, zinc, and lead, and so on. So why copper? For this research, I look into copper because copper is the third most abundant metals among all other essential heavy metals that we have. And basically, this is like a procedure of what I the fluorescence compound, which is the rhodamine compound that I use. And that this is like when the metal is attached to the or binds with the non-fluorescent compound. Once it binds, there is the signal which shows a fluorescent, which shows like a light is being identified, and this is when the binding occurs. And rhodamine dyes, we make use of rhodamine dye because of their properties. They are high
They have high visibility region, they have high wavelengths and absorbance, and they have high quantum yield as well. This is one of the reasons why we use of the energy. And another thing is that they are very they are low cost, they are not expensive to get. And also the synthesis as well, it's very easy to make to synthesize this compound as well. So the method I use this method, which is a microwave assisted synthesis to synthesize my rhodamine dye. And the main reason why I use the synthesis is because there are other conventional synthesis that has been used, but what happens is that the time that they use, they spend up to like 1 hour, 2 hours, 3 hours to get their result. But I make use of this instrument because it's very fast, it's easy, it's simple to use, and in 20 minutes, 30 minutes, I can get my results, and also it gives me a very good yield. The yield I get out of my the synthesis are very good and also very useful. And another thing I did in my application is preparation of titanium dioxide, which most people have talked about, and also the fabrication of the diagram, the size of the cell. Those are the things I also prepared during the scope research. So my synthesis is in 2 phases. The first one is, this is the hydrazine. This is the one I purchased. So the first one is a reflux reaction. I did a reflux reaction because like a condensation reaction where I want the reaction to be complete. So I use the reflux so that I can have, because of high temperature, I needed a high temperature to break this bond so the water can actually lead this reaction. So in the presence of ethanol, I reflux this to get my rhodamine hydrazine. So this is the result that I reacted almost all the 20 aldehyde that I used. So these are like 3, I'm presenting like 3 aldehydes today. I reacted this aldehyde with this. This is like a benzene ring attached with like a pyridine, yeah. And I call it P15, which is part of the name of the compound is aldehyde. Okay, it's a phenyl compound attached to the benzene, sorry. The name of the compound is aldehyde. So if I reacted these products into 1:2 ratio. Okay. I attach it into 1:2 ratio. So 2 of rhodamine, this is 1, this is 2, attaching with the aldehyde. And this is the furan compound. I call it P41. Also 1:2 ratio, ratio. And also the P45, the P45, that is the 5-hydroxyl methyl furan. So it is 1:1. So I use those 3 compounds because I want to see some similarities, I want to see some differences that it has in my application as well. So from the result, I did I did optical activities for my compound, and I used UV and fluorescence spectrophotometer, and I use them simultaneously. Once I'm using the UV, I make sure I use that same compound with my fluorescence so that I can get like a similar results. And so when I did for the 3 compounds, I found out that this compound was selective for copper ion and also shows a little absorbance for mercury. But I focus on copper here because the mercury did not give me a high absorbance, and it did not show any color change. So I only found color change with copper. So this is the fluorescence and also the UV. And these are the other metals that I reacted it with.
These are the other metals are also used, but it shows selectivity for copper alone. So another thing I did is to check for the fluorescence lifetime, because I want to check the lifetime that this my compound spent from the excited state to the ground state. So I tried using the compound alone and also with attaching copper to heat to see the lifetime of each of this compound. And I found out that with copper, the P15 have the highest lifetime, followed by the P41 and P45 with copper attached to heat. So definitely copper, the presence of copper with this compound shows an impact in the lifetime and also in the lifetime of this compound as well. Yeah. So another thing I check is to check for the current and voltage measurements. To confirm the solar energy to electric energy, to confirm the efficiency of my compound being able to convert from solar energy to electric energy, it's needed for me to measure the current and the voltage measurements of this compound. So I measure the current and voltage measurements, and looking at this diagram, we can see that with copper, it's higher. It's higher than without copper. And also for the P45, this is with copper and this is without copper. And also for P41 as well, without copper, and this is with copper. So definitely with copper has helped to increase the efficiency and also the impact of my compound to solar cell, and also as show some electron transfer as well within this compound, and which could be effective as a synthesizer for solar cell. So another thing to confirm is to confirm the quality of the charge and also to confirm the properties of this charge. And I also did that by measuring the impedance of my compound, and which I did here. We can see how the electron is being transferred, the combinations of electrons, and also this proves this proves and shows the efficiency of my compound as a synthesizer in solar cell. So in summary, a new compound has been detected, and we have synthesized this new compound. And the good thing is that we found out that this compound is selective for copper among every other essential heavy metals that we tested it with, which is a good one. And we are planning on publishing a paper on this, and it's going on already. It's we're almost done with the manuscript as well. So, and another thing we did to confirm the purity of this compound is that we characterize them using NMR, carbon NMR, and high resolution mass spec. And all this confirms the functional groups, confirms the number of protons, confirms the number of carbons, and also the mass number of our compound. And this shows how the purity of our compounds as well. And also the solar to electric power efficiency of the complexes of rhodamine dyes were higher than that of only the rhodamine dyes without the copper or metal ion attached to it. So I would like to thank Dr. Udin, who's not here, my supervisor, Dr. Gaim. Thank you for your support and every assistance that I need on this research to work more with people. Thank you so much.
Okay, so our next speaker will be Samson. Okay, now we can share this lecture. Samson, can you hear us? Can you hear me? Samson?
Yes, I can hear you.
Okay, good.
Can you see my screen?
So it's your floor. Yes, we can see your slide.
So again, my name is Samson Gichuki from Morgan State University. I work with cyanobacteria in Dr. Sitha's lab. Today I'll be presenting to you some of the work that I'm doing, which the title is Ion Nanoparticle-Induced Oxidative Stress in Flammida diplocyphon using Immunodetection and Lipid Paradoxation Assay. So, I'll give you some background, especially for the high school students, so that they're able to understand how research is conducted, and kind of give you I see most of you are very good, and I would like to applaud you, all of you, for doing an excellent job. So in spite of iron being important for various processes in cyanobacteria and many bacteria, its bioavailability is a growth limiting factor, basically meaning that its availability to be used in the biological processes inhibits the growth, or it's a limiting factor. So nano 425S, which is the nanoparticle that I'm using, zero-valent ion nanoparticle I'm using, has been proposed to be a new miracle due to its ability to be available for the bacteria to use. It has been shown both in this lab and other researchers that it enhances growth and leads to also accumulation of unsaturated fatty acid, methyl ester, therefore improving biodiesel capability. So in our lab, we are focusing on renewable sources from cyanobacteria, and therefore this is very important to us. However, the toxic potential of NZVIS is still unknown, and therefore this is where my research comes in. So a little bit background on cyanobacteria. Flammida diplocyphon is the model organism that we use here. It's very good because it can go very fast and rapid biomass production. Within 7 days, you're able to produce one culture, 7 to 10 days. It also has the ability to grow in low light intensity due to something called complementary chromatic adaptation. We have engineered this strain for salt tolerance and also enhanced lipid production. As you can see, the picture there, that is a plate. I had a plate here to show you, but I don't think you can see me because I'm sharing my screen. And the middle picture there is how we grow it in a liquid culture. If you saw my background, is the shaker that we grow into in it. And then right there on the farthest right, see, it's a very good picture that we got from Dr. Udin's lab, and it's a good picture that we are able to. You're gonna see some more pictures later on. So the way I conduct my experiment is to, first of all, you grow bacteria, cyanobacteria, in liquid cultures containing NZVIs, ranging on various concentration. For the purpose of this study, we did 0.8 milligrams per liter to 100.2 milligrams per liter. After 15 days of incubation, we determined lipid paradoxation, and also we quantified using immunodetection ion superoxidase dismutase. As a good experimental setup, we always have to have 3 replicates treatments and also have a control. The control for my study was the cultures that were not exposed to NZVIs. Data was analyzed using ANOVA 1 way, took it on a significant difference, because in science, if you don't have a way to analyze your data in a way that's gonna prove that your result is legit, then you'll not publish any papers. So on the 4th day and the 12th and 20th day of incubation using specifically 3.2 of NZVIs, we took transmission electron microscopy images, which was also equipped with, give me a second, which was also equipped with EDS, that's elemental analysis, for elemental analysis. So our data, and again, this is just because I know we have a lot of, I try to make it simple for all of us to understand, especially for the high school students. So we did for the anti-ion superoxide dismutase, we did an analysis, which I referred to the immunodetection. And this revealed that the highest concentration for this specific experiment was 51.2, and it had the most superoxidase dismutase levels. And also in when you looked at 6.4 milligrams per liter, also it exhibited higher significant level than 3.2, and of course control. So what the point that you have to take away from here is that NZVIs increased SOD production in the cell in a dose-dependent manner. Okay. So this is also I should have mentioned we are working on 2 strains, which is one is the wild type and one is the SD, as you can see the 4th point. The SD strain has high lipid content, and also because they're different strains, they behave differently. Validation of NZVIs in tree culture using the EDS also reveal a strong ion peak on the 4th and the 12th day. Simply when you incubate the cells with NZVIs, we see that on the 4th day there's more uptake of these NZVIs, also on the 12th day, and then on the 20th day we see a sharp decrease, meaning it was uptaken by the cells. So this is a graph showing you immunodetection of ion superoxidase dismutase. A is a gel picture that shows different concentrations of when we incubated with NZVIs. And on the right is just a graph that I did as an analysis so that we can be able to see the significant differences. And as you can see, the blue one here is the wild type, and we see that we have more SOD compared to the SD strain. And this is mostly uniform throughout the treatment, other than the 51.2 where we saw a bit difference. Another thing that we quantified is malaldehyde. This is also called as MDA, cellular content. And we found that there was an increase in MDA content in the cell the more we increase the nanoparticles. And as you can see, control has the least amount of MDA. And MDA simply is a lipid productivation. It's a measure when lipid breaks down because of oxidative stress. And that's what we are measuring. And we see that it's caused in an increasing manner. I know we can see the last reading, the last bar graph here is 102.4 milligrams per liter. And we see a significant, we can say it's about the same with control. But what we found out is that once we increase nanoparticle to this high concentration, they basically, the cells die, they do not grow, and therefore we see the starting material to quantify, and therefore it gives you a very low MDA content. So this is some of the results that we worked with Dr. Udin together with his team, and over and over I've had most of the students saying the size of the nanoparticles that is between 10 to 100 and nanometers, and now here we see we're able to send these samples to Dr. Udin, and he's able to get some good transmission electron microscopy images. And as you see, I don't know if you can be able to see, but the first image on the top left, it gives you the average sizes of all the individual nanoparticles. And this is the power of electron microscopy. And then on the blue side, which is the right side, that is the EDS, and it's showing the 4th, the 12th day, and the bottom was the 20th day. And as I said earlier, on the 4th and the 12th day, we see the highest concentration of ion, elemental ion within the cells. And on the 20th day, we see it a sharp decrease. So our finding also indicated that, so this is kind of concluding and making sense of our data. Our finding indicated that NZVIs in both strains, wild type and SD of the Flammarion diplocyphon, induce ROS generation in a dose-dependent manner. We already know from literature that when NZVI reacts with water or oxygen, it produces redox active ion, which also will generate highly reactive hydroxide radicals. This is what causes the oxidative stress within microbial cells. So results also reveal that higher concentration led to elevated ROS, as I said, and also increase in MDA content, which is lipid productivation. Elemental ion concentration increased in the culture at the 12th day of incubation, showing a localization. One thing we want to understand is to see if the bacteria are uptaking this cyanobacteria. Our future work will be going towards understanding the mechanisms that are involved in the uptake and the localization of NZVIs within Flammarion flow siphon, and also to perform gene profiling analysis to see what other genes are being turned on or being turned off. I'd like to thank Dr. Sida, who is my research advisor, Dr. Udin, William, and Dr. Kang for supporting this work, and also my lab members, Dr. Yasin, Ladonna White, and Christian. Also, everything needs money, and we found our funding from the NSF, which was awarded to Dr. Sida. Thank you very much.
Thank you, Samson. You did a nice presentation, and I'm sure that Dr. Sither Group, you're doing very good. You have, let's clap him from here. And he has already 2 papers. One paper we published in the SCS, American Chemical Society Journal, very good journal. And another one is same journal we, Dr. Sither and our group worked, and then we submitted. It's on the way, isn't it, Samson?
Yes.
Yeah. So what's your plan next, Samson, after that?
You mean after finishing or with the
after
study?
finishing your PhD? What's your plan?
I'd like to continue my research and also maybe go back to the university and teach.
That means you want to go plan for a postdoc?
Exactly. Thank you.
Okay, good. Wonderful. So how long you have time to defend your PhD?
So we are still in the process of looking to that, but maybe about a year or so.
Okay. So now let's go to the, yeah, thank you.
Go ahead.
Yeah, any question from the audience or in the virtually? Anybody? Any question? No question? Okay. Anything from virtually? No? So Samson, and thank you so much that we'll continue our research as electron microscope part. We are helping Samson and Dr. Sither to to improve his research article. And I'm sure Tolu and Samson is a very good addition. And another person, just fresh PhD student, she's also working with Dr. Sither. She's coming to work also. And in future, I'm pretty sure we have a plan to actually, I want to tell those who are in virtually all over the world. I know somebody's from Malaysia, somebody is Saudi Arabia, I can see their name, somebody in Bangladesh. Thank you so much for all the scientists and professor you're listening until now. And then I'm pretty sure that this collaboration, we have not only nationwide collaboration, we have international collaboration also. This year we published, even though it's a pandemic year, around 20 papers, peer-reviewed and highly impact journal we published. If you go to our journal, sorry, website, you can see. And also some of the papers are on the way. And then I'm really very much interested to work with Morgan because there are 3-4 professors working with me right now. Their dean, he was dean actually, now he's a provost, Dr. Yu, is a very good researcher, as well as he push always to work his professor and student. And I'm pretty sure this culture will continue in our Coffin state as well. So this is actually ending our high school, undergrad, and graduate student presentation. I hope this presentation, you liked it, and there are still so many people and students, some student goes to their class and come back again. And then I really appreciated your passionately you are in the room, and then you listen all of our children's or kids presentation. Now before we go to the lunch, we have a light lunch. I would like to, as I promised in the announcement, that we'll, even though I think it was very difficult for me, maybe Dr. Nesbitt, our chemistry coordinator, tell a little bit about how difficult it was to judge, but ultimately we have to judge first, second, third. Huh? So let's see that how it goes. Can you announce it? Yeah, because I am worried to announce it. You know, I want somebody to announce. Yeah, please. And I'll give you their award certificate. And you have some, those are first, second, third, fourth. You have some, what do you call it? Gift card, maybe you can use. Okay, okay, go ahead, Dr. Please.
Good evening, everyone, and welcome. It was really hard judging these. You guys did an excellent job, really an excellent job. And as they indicated, you're the ones that will be solving the problems of the future for us, the problems that we're having, you know, with global warming, having enough energy. So you're on the right path. You know, you're taking the right steps to be able to solve those problems. But we did have to come up with a first, second, and third. So here are the results. In first place is Haseen.
Haseen Hussein. Huh?
Yes.
Haseen Hussein. Okay, that's it. Come on, come on. Come on. Can you take the picture of him? Haseen Hussein is the first. Goes to, according to the judges, 5 of the judges. So this is the first place award, and this is the award. I hope I put the right one, but I want to check. Yeah, that's fine. So your gift card, okay? So take it and then, then take the picture. Yeah, show them. Okay. Thank you. Good job. Okay, one more. Okay. Can you bring those? Okay. So that's the medal. Go ahead. Next,
Second place is Reza.
Afrin Reza. Second place. Come on. Yes. Afrin is the second prize. Okay. So this is your certificate, and Dr. Sobi is giving your medal here. Please.
Yeah.
Good job, everybody. Good job, really. It's very hard for them. Okay. Yes.
I need some help with the third one. Oh yes. Third place is Saha.
Saha, Vital Saha. Okay. So actually, it was very close.
Yes.
It was very close for that company.
It was kind of tight.
Yeah, it was very, very difficult for us. Yeah, take the picture. Take it. Okay. Okay. Good, thank you. Okay, then fourth place also we have prize. Hi, Dr. Bas. No.
First place is Noor Fabrali.
Yes.
Graduation.
So many certificates.
Chica.
Yeah, there are so many certificates. I'm sorry. Okay, anyway, I'll give it to you later. You can go. Thank you so much. Can you take the picture? You got it. Oh, you got it. Okay. Here you go. No, this is not okay. Okay, so take the picture. I'll give you. Okay. Okay, thank you. Next, so this is for high school student. Thank you so much, Doctor. It was really, really very competitive. We want to see the score. He has score also, but very good job. You did very good. Now let's go to the. I want to give the certificate for our undergrad and grad student, those who work. So come on, Beatrice, please see that Beatrice and certificate on one. Here, you can see that. No, not this. Very difficult somewhere. Yeah, Balbin, you can come first. See that. Coulomb, Beatrice, Balbin, everyone is. You can come. Beatrice, William, you can come. Beatrice, you need to come to in the picture. You know, come here. Okay. Next is Beatrice. Can you take the picture? Here you can come. Thank you. Thank you. Good job. Beatrice. Okay, Beatrice. Good job. Just continue to work, okay? Work is not finished yet. Okay, next is Ruth Coulomb. Is Coulomb here? Where is William? I want him to picture with that. Yes, this is not him. This is Coulomb. Yeah, next. You find that there is there. Everything is there. No, Chika is not there. He's there. Okay? Take it. Okay, thank you. Ruth is here. Then Naina. Naina, you see that here. It's coming here. Thanks, Ruth. Good job. Naina is here. Keep all professors certificate with you. No, not this one. No. Yes. Yeah. No. No. You can come. Okay. Now, next is Naya. Yeah. No. We got your certificate. Sorry for that. Yeah. It's few certificates we have to find out. Okay. Take a look. Thank you. Come on. Naya, you have to work hard. She's a chemistry major. I always push her to work. Okay? Good job. Okay, then our graduate student, Tolu. Come on. Good job. Tolu is coming every other day to work from Morgan here with William. So she's accumulating lots of data. And Samson, your certificate and medal will be given later, okay? Samson, are you there? Maybe he's not there. Okay, so we are done now. We would like to give our judges for their certificate. They worked hard. So let's go to the Dr. Nesbitt, huh? Dr. Nesbitt, who is first? Okay, you can go. Dr. Nesbitt, please. No one to take the picture? He's gone. Can we take the picture? Come on. Come. He's gone. Oh, he likes the student. Okay. So take the picture. Yeah. Okay. Because this is a record, you know. Okay, one by one. Dr. Nesbitt, thank you so much for your cooperation. Always you do. Thank you. One is fine.
Mano. Come with us. Come take the picture with everybody. It's our group. Yeah, you have to take continuously, okay? Until you finish. Okay? Go ahead. Okay? Good, thank you. Stand there. Next, okay, who is this?
Dr. Jarvis?
Savage is here. Yes, thank you, my friend, for a long time. Okay? Thanks, Dr. Sully, for your work. Yeah, next.
Dr. Bailey?
Dr. Bailey is not here. We'll give later.
Dr.
Yeah, I don't think
Dr. Raj?
Raj is not here. And then,
That's me.
yeah, yes, okay.
Me.
Okay, please come in. Now, my friend, Dr. Henny Sovi. So, thank you. All three are three students, chemistry professor. Okay. Thank you.
Thank you.
Thank you so much. Okay. So, yeah, I'll make one for you. So, I'm not prepared. Give me his name. Okay. And then we'll make for one. So, anyway, thank you so much. Still few people left, and I really appreciate it. And then I'd like to introduce our new faculty here. So I don't know you know him. Can you please, Iqbal, Rauf Iqbal? So can you introduce yourself, please, little bit? Yeah, thank you for coming, even though you're not in the science.
Hello everyone. My name is Ghazi Iqbal, and I am an assistant professor in the College of Business here at Coffin State University. So I joined here in spring semester, and I came to know him from my cricket group that there is a big shot guy working at Coffin. So I came to and I introduced myself here. And my research is I'm basically from engineering background. I did my bachelor in industrial engineering, bachelor, PhD, master's, everything. And now I am doing data science related area like optimization data science. Thank you, Dr. Uddin.
Thank you so much, Dr. Iqbal. Welcome to our Coffin. I see that our sponsor research officer, Dr. Bas, please come in forward. You want to talk something because I really appreciate that you come in and say a few words, please.
Good afternoon, everyone. My name is Diana Voss. I work in sponsored programs and research, and I just want to say on behalf of the administration of Coppin State University, this is a really benchmark program, and just really enjoy sponsoring and celebrating because this is really the next generation of researchers and really kind of epitomizes what being a student here and what being a faculty member and really most importantly what being a staff member means to be at Coppin State University. So and really I work with Dr. Uden on grant proposals, and we have collaborated on Constellation Energy proposal since I joined Coppin 4 years ago. So this is, a lot of work that every faculty member in the Department of Natural Sciences makes happen. And we hope that it's been a warm and welcoming event for each and every one of you. So thank you for your hard work.
Okay, give a big clap, please. Okay, Dr. Bas is really, really working hard. And William always tell Dr. Bas that about you, that she works hard. So yes, please help us. And you're doing wonderful job for everybody, and I hope we'll continue our collaboration. So this is end. So I hope you like this event, and we'll continue. This is an annual event. So next year we'll do it again, and hopefully Constellation will give us continuous funding for that, and then we'll have more better research in our center. So thank you so much, everybody. So we have a light lunch, and those who are in the, I can see the still people are there. So thank you so much for your kind presence in this event. And I would like to invite you next year. Hopefully we'll have more better programs coming, even though COVID restriction, but still we are working. Our kids are working. They showed their data. This is their real data, real time. So I just want to appreciate all high school, undergrad, and grad student, those who presented today in this STEM Day event. Thank you so much. Okay, so we want to take a picture, Dr. Yes, Dr. Sobi told that, would you please come? We can stand here, then we can take a picture. Yeah, thank you. Please come. Take a group picture. William, come on. Take a picture. Come on. The phone is here.
Only the faculty or the guests.
One more thing I forgot. Here, one professor is here. Dr. Obaid Beg is here. He came. I invited him to come to see that, and he was gentleman. Quietly sit down here all time. Thank you so much for coming. Could you please still talk about little bit?
It's Obaid Beg, not a faculty here, but I'm a faculty overseas in Pakistan. I do biological sciences actually, so I'm biochemist.
We have a picture. It's a group picture. Can you come? You have to. No, we put it in the website. Come on, guys. Man.
Yes.
Yeah, no, come here. Come here. Those who are tall backside, go. It's too a little bit close. Okay, student. Yeah. Student Ryan, go there. Student first.
You guys.
Come. Yeah. All the students need to be. Yeah, you can put it here if you want. Yes, come on. Yeah. Tolu. Acha, who will take this picture? Let me take the picture. You want to take picture? Yeah, come on. Come on. Here. Come on. And then this is my phone, so you can take the picture. Okay, so take few and panorama this side from here. You cover okay? Okay, guys. Okay. You want? Huh? Oh, okay. So here, like that.
Yes.
Those are fun. You can sit down. You can see. It's okay. Yeah.
Yeah. Cheese.
Cheese.
Smile nice, everybody.
Smile.
I'm about to fall.
Better be good.
Okay. Thank you all. Okay, food is there. Excuse me, everybody, please go there outside and see the food. William, can you? Yeah. You sign a sheet? Yeah, it's fine. If you're fine, you are fine. Okay?
You get a phone. Take a picture, you get a phone.
Yeah, but
Yeah.
I got.
Yeah, lunch is there. Everybody, William, go there first.
You're Abdurrahman, right?
Yeah. What size is it? That'll be.